Here are solutions to homework set number 14 for ECE 341. This homework looks at chi-squared tests. Now the chi-squared test is a test of a distribution. The idea is to collect some data, compare the data to the assumed distribution, and see if they're consistent. For example, here is some MATLAB code that generates a number 1 through 6, basically a six-sided die. Is that a fair six-sided die? Do all numbers have a 1 in 6 chance of coming up? Well, to determine that, I run a chi-squared test. The first step is to collect some data. So here I rolled the dice 240 times. And when I did that, I got this many 1s, this many 2s, 3s, 4s, 5s, and 6s. Now I calculate the chi-squared value. What you do is you separate the data into bins. I chose each number as a bin. Take the probability of landing in each bin. If it's a fair die, it should be 1 in 6 chance. N times P is 240 times 1/6. I should get 40 in each bin. Here's how many I actually got. The chi-squared value is take the difference squared divided by 40. So 0 squared over 40 is 0, 4 squared over 40, 0.4, 2 squared over 40, 0.1, and so on. Add them all up, I get a chi-squared value of 0.85. Now to convert that to a probability, I use a chi-squared table or a stat track. I've got 6 bins, meaning 5 degrees of freedom. My chi-squared value is 0.85, and that means 2.6%. So there is a 2.6% chance that this is not a fair die. Problem 2. This is a loaded die. 5% of the time I roll a 6 no matter what. The rest of the time it's fair. Can I detect that this is a loaded die with 240 die rolls? Again, it's the same procedure. I assume it's a fair die. Each number should come up the same number of times. Collect some data. I got this many 1s, 2s, 3s, 4s, 5s, and 6s. Now compare. The difference squared over 40. 3 squared over 40, 0.225. 3 squared over 40, 5 squared over 40. Add them all up. Chi-squared value is 3.15. Now to convert that to a probability, again I go to a chi-squared table or a stat track. I have 6 bins, meaning 5 degrees of freedom. My chi-squared value is 3.15, corresponds to a probability of 32%. So with 240 die rolls, I'm only 32% certain that this is not a fair die. Basically, I can't detect 5% loading with 240 die rolls. You probably can't. Suppose I had 1,000 die rolls. Then could I detect it? So same procedure as before, but now roll the dice 1,000 times. Here I got this many 1s, 2s, 3s, 4s, 5s, and 6s. Put them in a chi-squared table, take the difference squared, divide by expected value, add them all up. I now got 11. Converting 11, chi-squared value of 11 to a probability, I've got 5 bins, chi-squared value is 11, 96% chance. So with 1,000 die rolls, I can be 96% certain that this is a loaded die. If you have enough data, I can detect any amount of loading, but it might take a lot of data. Problem 4. Checking to see if I'm psychic. Here what I did is I took a deck of playing cards, shuffled them, then predicted what the first card is. Hearts, diamonds, clubs, or spade. Flip it over, see if I'm right. Take the next card, guess hearts, diamonds, clubs, or spade. Flip it over, see if I'm right. Count how many times I'm right, how many times I'm wrong. I was correct 10 times, incorrect 42 times. The expected number is 13 and 39. There are 4 suits. I've got a 1 in 4 chance of being right, 3/4 chance of being wrong. Calculate the chi-squared value. The difference squared divided by 13, difference squared divided by 39, add them all up, get 0.92. Converting that to a probability, I've got 2 bins, meaning 1 degree freedom. My chi-squared value is 0.92, corresponds to 66%. So there's a 66% chance I'm not just guessing. Again, that's typical with the chi-squared value. If it's really large, like 99%, I can be pretty sure I'm not guessing. If it's really low, like 1%, I'm suspicious that I fudged the data, or I did something like I guess spades every time. 66% is kind of no conclusion. Problem 5. Well, if I take a uniform distribution that's uniform between 0 and 1, that's the rand function of MATLAB, add 3 of them together, what I get is this shape. That's the central limit theorem. It has a mean of 1.5, a standard deviation of 1/2. Can I tell the difference between this and a normal distribution with the same mean, same standard deviation? Well, the procedure is to first collect some data. I collected 100 values for y. Again, that's kind of arbitrary. I chose 100. I then split the data into n bins. That's also arbitrary. How you split this up? What I did is I chose every standard deviation. So 1.5, 1, 0.5, and 0. Likewise on the plus side. So those are my bins. I then count. How many times does the data lie in each bin? I then compare actual versus expected. Being a normal distribution, I know the area to the left. That's your z-score. Take the z-score at 1.5 versus 1. Or actually this is 0 in terms of standard deviations. What's the z-score between -1 and 0 standard deviations? -1, -2, and so on. And here's what you get. So there's the code. I roll the dice 100 times. Each time I roll it, I keep track of which bin the data lies in. And here are the results. This is what a normal distribution would look like that has a mean of 1.5, standard deviation of 0.5. Here's the expected frequency for bin number 1, 2, 3, 4, 5, and 6. The actual frequency. Now to see if the two are consistent, calculate the chi-squared score. So here's the actual frequency, here's the expected frequency. Difference squared divided by 2.275, difference squared divided by 13, add them all up, 4.25. I have 6 bins, meaning 5 degrees of freedom. Chi-squared value is 4.25, corresponding to a probability of 48%. And those numbers, again, 48% kind of means no conclusion. I have no evidence to say that this is not a normal distribution based upon this analysis. So that's kind of the central limit theorem. If I just add 3 uniform distributions, it's really hard to tell it from a normal distribution. It is not a normal distribution, but it's really hard to tell the difference. Number 6 looks at a Poisson approximation to a binomial distribution. If I roll 90 dice and count the number of ones, that's a binomial distribution. This gets kind of hard to calculate because I've got 90 factorial in there. A Poisson approximation says that lambda is n times p, n is 90, p is 1/6. So if I use a Poisson approximation where lambda is 15, these two should be roughly the same. This is a whole lot easier to calculate. Are they the same? Well, let's do a chi-square test and find out. I'm going to roll the dice 200 times, find the number of times I got 0 ones, 1 1, 2 1, 3 ones, compare to this, that's predicting how many times you should get 0 ones, 1 1, 2 1, 3 ones, and see if the two are consistent. So the first step is to collect some data. Here I rolled the dice 200 times. This is how many times I got a 1, 2, 3, 4, so on ones. And those are the blue stars. The Poisson approximation would be the red line. Are the two consistent? Well, the first step is to split it up into bins. I don't really have enough data for 30 bins. Again, you want a couple results in each bin. With 30 bins, I'm not getting a lot of results. So what I did is I grouped them into threes. So 0, 1, and 2 is one bin. 3, 4, 5 is another bin. 6, 7, 8 is another bin. So these are my bins. So there's my first bin, k is 0, 1, or 2, second bin, 3, 4, 5. This is kind of arbitrary how you group them. But I did that so I get a decent number of results in each bin. Here's the actual results. Here is the Poisson approximation. Add up k equals 0, 1, and 2, add up k equals 3, 4, and 5, add up k equals 6, 7, 8, times 200, that's n. Now calculate the chi-squared value. Take the difference squared divided by 0.04, difference squared divided by 1.48, difference squared divided by 12.44. Add them all up, I get 8.8. To see what that means, I've got 10 bins, meaning 9 degrees of freedom. Chi-squared value is 8.8, corresponds to 54%. And again, that means no conclusion. I don't have enough evidence to say that this is not a Poisson distribution. So that is a chi-square test. It's a test of a distribution. With it, I can tell whether a die is fair. I can tell whether data is a normal distribution, or similar to a normal distribution. I can tell whether data is a Poisson distribution. Homework set number 12 for summer 2023.